All right, class. I am going to be going through the probability worksheet step by step. Um, and I just went through it, and I don't think any of it got recorded. So I'm super fresh on this stuff. I've done this multiple times now. Okay, so we want to know for this first question, Beth and Shayna each purchase one raffle ticket. Okay. And if a total of 11 raffle tickets are sold and 2 winners will be selected, what is the probability that both Beth and Shayna win? Okay, so we're doing combinations and permutations right now. So we need to decide if order matters. And for this one, and I think for, you know, most of these, we can look at it in a certain way so that order doesn't matter. And that will uh, clean up our computations a little bit just because combinations are smaller numbers. So we're going to take, oh, and what is probability? Well, it's the size of the sample space, and we're going to divide that away from ways an event can happen, and that's going to be the probability of a particular event. As we've been doing these, I think I'm going to draw a few more pictures. So we have 2 tickets out of 11 that we want to pick. Okay, so we want to pick those tickets. And it looks like there's only one way to pick the 2 tickets, especially if we don't care what order we pick them in. So in total, the size of the sample, right, the sample space, it's going to be 11 choose 2 because we're picking 2 winners. And if we pick 2 particular winners, that's going to be like we picked just the right 2 out of 2. So this is in fact going to be our probability. And notice that 2 choose 2 is going to be equal to 1, right? So we could have just written this as 1 over 11 choose 2. Let's look at number 2. Ah, yes, the diplomats. Okay, gonna do another drawing for this. We have the diplomats, and there's 14 government officials and 1 diplomat. And of the 14 government officials, 4 are spies. So we've got our 4 spies here. And we've got our 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 government officials. If the diplomat gives secret information, I'm just going to call them not spies. Not spies. If the diplomat gives secret information to 10 of the attendees at random, what is the probability that no secret information was given to spies? Okay. Well, the only way to not give information to spies, since we're going to choose 10 of them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, there's only one way to do that, right? 10, choose 10. So if we're looking at the size of the sample space, we've got 14 officials, and we want to pick 10 of them. And there's only one way to pick all 10. 10, choose 10. This is, in fact, going to be the correct probability. Okay. Let's go to coin flipping. So, a fair coin is flipped 10 times. What is the probability of the coin landing heads up exactly 10 times? Well, we draw our tree diagram, right? And we get heads, tails, this branching pattern where at every new place we can pick 2 new ones, right? 2 more, 2 more, 2 more, and it's always going to be this branching pattern, right? Heads, tails, heads, tails. So we're looking for a pattern that would make this computation easier. And we're going to keep in mind that we have the fundamental counting principle. The fundamental counting principle says that if we have choices one after another, we can just multiply, right? So at the first branch, we have 2 choices. Then we have 2 choices. Then we have 2 choices. Well, we have repeated multiplication by 2. And how many coins are we going to flip? We're going to flip 10 of them. We want to know the probability of the coin landing heads up exactly 10 times. Well, we want to pick 10 of the coins to be heads. Do we care what order? No, I don't think we do, right? Because as long as they come up in any order that where we get 6 heads, that's going to be good. So I think it's going to be 10, choose 6. And it turns out that is the correct answer. Okay. So a 6-sided die is rolled 6 times. So right off the bat, I'm thinking about computing the size of our sample space so I can get our denominator here. 6-sided die is rolled 6 times. So we have this branching 1, 2, 3, 4, 5, 6. And if you can see, it's just like our other tree diagram, except each time we're going to go, right, 6, 1, 2, 3, 4, 5, 6. We always have 6 choices each time we roll a new die. And we're going to do this 6 times. So 6 layers of 6 choices each. That's going to be 6 to the 6 factorial. Now, the dice can be even or odd, and we want to pick 2 of them to be even. So we're going to do 6, choose 2. But how many possible ways could those even dice come up? Well, we're going to count all the even possibilities. 2, 4, 6. That would be even. So we're going to have 3 choices for the 2 dice. So it's going to be 3 times 2. But we're also going to have the odd dice, which can include our count, where we could have 1, 3, or 5 as odd numbers. So again, we have 3 choices, except for the 4 other die. So it should be 3 to the 4. All in all, you can see that we're going to have just 3 to the 6. But remember in class that we did this a little bit differently because you can look at this as a coin flip, right? Each 6-sided die has a 50-50 chance of coming up even or odd. So it's just like a coin. So if we count this like a coin, it should work just the same. So instead of thinking about branching 6 different times, we can think about even, odd, even, odd. And I think it should be clear now that we have the same pattern as the coin, so we can do 2 to the 6. And now we don't have to worry about these counts, right? Because, well, the dice are only coming up even or odd, and that's what we're considering. So again, we want to choose 2 of them out of 6 to be even, and then we don't have to worry about this right here. But actually, if we know exponent rules, and we know that 6 factors into 2 or 3, hopefully you can notice something, right? If I rewrite 6 as, oh, that didn't work. If I rewrite 6 as 2 times 3, we know a little bit about exponent rules. Exponents break up over multiplication. So I'm going to get 2 to the 6 times 3 to the 6. Oh, but what do you know? I have the same factor here and here. So this cancels. Oh, we counted 2 different ways and got the same probability. I think I can be very certain that this is the correct answer. Nice. Okay. 9 true or false questions. A test consists of 9 true-false questions. A student who forgot to study guesses randomly on every question. What is the probability that the student answers at least 2 questions correctly? Okay, so at least 2. Well, there's only 2 ways they could fail that, but there's a lot of ways that they could succeed. So I think we want to count the number of ways we could fail and then subtract that from 1 to get the complement. We did this in class. So 1 subtracted by, okay, something divided by something. And we're going to add 2 probabilities together. Okay, so how many different ways are there to get true false? Beating a dead horse here, right? But see, I start drawing heads and tails again. No, but it's the same thing. True, false. True, false. At each question, true, false, right? This is the coin situation again. So instead of 10 coins, we have 9 true or false questions. And how could we get less than 2 questions correct? Well, we could get 0 out of 9. So 9, choose 0. But we could also get what? 1 question correct. 9, choose 1. And those are all the ways we could fail to get at least 2 questions correct. So this complement is going to be at least 2 questions correct. Okay, let's move on to 6. A basketball player has a 50% chance of making each free throw. 50% chance, this is already looking like another coin problem. What is the probability that the player makes at least 11 out of 12 free throws? Okay. Right? In, out. Tree diagram. In, out. Wow, we're branching again, and we have 2. I hope you're seeing the pattern now, right? So what is going to go on our denominator? 2 to the 12. A basketball player has a 50% chance of making each free throw. What is the probability that the player makes at least 11 out of 12? Well, they could make 11 out of 12, or they could make 12 out of 12. So, seems like another choose, because we don't care which baskets we make. 12, choose 11, plus 12, choose 12. Going to be our probability. Keep moving. How much money am I making? Mason, you can donate some money, especially since you're going to be the next LeBron James. If you have any questions, please ask. Okay, so a technician is launching fireworks near the end of a show. Of the remaining 14 fireworks, 9 are blue and 5 are red. So I'm gonna draw another picture here, and I have 1, 2, 3, 4, 5, 6, or 5, 6, 7, 8, 9 blue fireworks. And I have 1, 2, 3, 4, 5 red fireworks. So in total, 9 plus 5, I have 14 fireworks. So if I'm looking for my denominator again, I'm going to launch 6 of them, right? So 14, choose 6. And we're going to pick exactly 4 to be blue. 1, 2, 3, 4. Well, that's one of the ways, but we want to count all the ways. I don't think we care which order these blue ones go off in. So 9, choose 4. But I'm firing 6, so I need to fire 2 more. So that means I need to pick 2 red. So using the fundamental counting principle, I'll just multiply those 2 to get all the possibilities and get 5, choose 2, because I need to launch 2 more fireworks. By the way, if we were to tree diagram that, if we were to tree diagram that, there's a lot more choices, and then As we shoot a firework, we expend one, right? So it's a little bit different than some of the other ones. But the jar question is just like the fireworks question. So we've got 10 black buttons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 1, 2, 3, 4, 5, 6 brown buttons. Black buttons, brown buttons. How many are we picking in total? We're picking 9, and we want to pick exactly 5 black buttons. So 1, 2, 3, 4, 5. And well, we want to pick 9, so we got to pick 1, 2, 3, 4 brown. So in total, we're picking from, what did we say? 10 and 6, so there's 16 buttons. Choose 9. And then we want to count the black buttons, which is, we're going to have 10. Choose 1, 2, 3, 4, 5. And 6. Choose 1, 2, 3, 4. Okay. Now we have what I think is the hardest question on here. The first way that I think about this is that I think like order matters here, but the same. So note that a standard deck of cards, a standard deck has 52 cards and 4 of those are kings. What is the probability that you'll have at most 3 kings in your hand? At most. So the only way that we can get more than 3 kings is to have all 4 kings. So we could have 1, 2, 3, 4 kings. And that's going to leave us with how many other cards? 48 others. Right? 1, 2, 3, 4, 5, 6, 7, 8. I'm not going to draw all these, right? But there's a lot of them. There's 48. And we want to pick all 4 kings if we want to count having more than 3, and then just one of the 48. So how can we represent that? Well, we can have 52, choose 5 different cards, and then 4 kings, choose all 4 of them, times 48, choose 1. And then we're going to subtract that from 1 to get our probability. And that's the probability we'll have at most 3 kings in our hand. Because all the other possibilities are 3, 2, or 1 kings, right? And the only other way is with these 4 kings. Okay, finally, we have something again that is very similar to the fireworks question, right? So this is just a reskin of the fireworks question. How many diamonds in total? Well, we have 6 real and 5 fake. So we have 11. And how many are we picking? We're picking 6 from the bag, right? So 11, choose 6. And then what is the probability that at most 4 of them are real? So the only way we could get more is if we had 5 or 6. So let's do the complement again. 6, choose 5. And then we also need to consider the fact that we're picking one of the fake diamonds. So 5, choose 1. Plus, well, 6, choose 6. If they're all real. And 5, choose 0, that's just 1 again, right? Subtract this from 1, that's our complement. And we are done with probability. This went over some questions that are even a little bit harder. Just remember that we're looking for when order matters and when it doesn't. But because we're dividing away a lot of things, you can either count with order, without order, right? We could also consider that we could count this with order, and it's going to end up being the same thing. Like this whole expression, we could count it with permutes instead of combinations. And yeah, that would be fine, but I think this is just ends up being easier. All right.